Hello everyone, hi and welcome you all on Physics Adhan. So in the previous last video, we have just started to revise the topic of entropy and the second law of thermodynamics. So in this particular video, I will try to complete the entropy change in different processes and I will start the thermodynamic potentials. Okay, so let's get started by the topic that is change in entropy when two bodies are in contact. Okay, so this is our today's right now topic, and we know what kind of contact we can have. So we can have a reservoir, and or it can be a body. So there can be possible three combinations. We can have reservoir to reservoir contact, or we can have reservoir to any body contact, or we can have body with body contact. Okay, so three different type of processes can be happen. So let's look first, that is reservoir to reservoir. Let's me call at two reservoirs. Let's say R1 and R2 are in contact at different temperatures. Let's say at T1 and T2. So let me suppose there are two reservoirs. So this reservoir is R1, this reservoir is R2. Let's say this is a temperature T1, this is a temperature T2, and I have a condition that T1 is greater than T2. So what will happen, there will be a flow of heat energy from this reservoir which is at temperature T1 to a reservoir R2 which is at temperature T2. So let's say that the heat transfer is Q. So what will be the my entropy change for these different reservoirs? So let me start with reservoir 1. So reservoir is giving heat to reservoir 2. So I'm writing this as minus Q by T1, and reservoir 2 is getting heat, so I can write that delta Ts2 is Q by T2. Okay, this totally depends upon a convention. I usually take, if someone heat is extracted from the system, I take it as a negative. If some heat is given to the system, I take it as a positive. So the total entropy change is Q. You can take common 1 by T2 minus 1 by T1. Since T1 is greater than T2, so this quantity is going to be greater than 0. So the delta S total for this reservoir to reservoir contact is greater than 0 and given by this formula. Okay. Now we have seen reservoir to reservoir. Now let's see reservoir to body contact. So now we have reservoir to body contact. So what will happen in this case? Suppose the same system, I have a reservoir over here and I have a body over here. Let me call this reservoir as has temperature TR to just denote that this is a temperature of a reservoir and this is the temperature of body, and I am saying that temperature of a reservoir is greater than temperature of the body. Okay, because reservoirs can get infinite number of amount of energy without changing in temperature. That's the basic idea of the reservoir. Okay, so it can only transfer the heat from reservoir to the body if this Tr is greater than Tb. So now let's accept again this amount of energy Q is given to the system. Then there will be a heat flow and the energy is Q. So this energy will flow until and unless this body gets temperature from T body to T reservoir. Until this heat will flow. When the temperature of reservoir and body will be the same, then the heat flow will stop. Okay, now let's calculate the change in entropy for the body. So delta S for the body is nothing but dq by T, dq by T. Okay, so it is gaining the heat. So it is heat gain. So now delta Q, heat gain of a system, is given by ms delta T. Okay, ms dt. So dt is a temperature difference. So this is ms dt by T integration, where S is a specific heat as discussed in the previous video. So this is ms, and this limit will be from Tb to Tr because this body is getting temperature from Tb to Tr. So this is ms, and this will be a logarithmic function. So this is log of Tr by Tb. Since Tr is greater than Tb, so this function is always going to be greater than 0. Okay, the whole delta Sb. Now we have calculated the delta Sr for the previous. So this was integration of dq the heat gain, the heat loss by the reservoir at the temperature Tr. Since Tr is constant, so you can take Tr to be outside. Now, what is the amount of heat that is lost by this reservoir? Okay, I'm saying loss, so it means there is an intrinsic negative sign. So the energy gain, sorry, the total heat gain by this body will be, the total heat gain by this body Q will be ms times Tr minus Tb. So this is the heat gain by this body. So the heat lost by this reservoir will be this. So I am taking an overall negative sign because of my convention, and you can write here as, sorry, ms. This is ms Tr minus Tb. So this overall will be minus, or you can change minus sign inside. So it will be Tb minus Tr into ms by Tr. Okay, so this is the second case. So that's it. So total change in entropy will be delta S of B plus delta S of R. I'm assuming that there is no change in entropy in the surrounding. So this will be the universe, the entropy of the universe, the whole surrounding. If there is no change in entropy in the surrounding, then the only system you are left with is a body and a reservoir. So delta S universe will be delta S body plus the reservoir. And reservoir is given by this and body is given by this. I hope you get an idea how to calculate. So body dq heat gain is msdt. Msdt you integrate from what temperature to what temperature it is going. And for reservoir, since it is, this Tr is constant, take this Tr to be common. And what is the heat lost by this reservoir, and that we have calculated how much heat is gained by the body. So that much amount of negative sign will be the heat lost by the reservoir. Okay, and this question particularly was asked in this year 2019 December net examination. This alpha and msdt cvdt, the value was different, but the concept, overall concept was the same. Okay, now there can be another situation when you have two bodies in contact, two bodies in contact. So I'm not going to do the whole formal because you get an idea from the previous two examples. So let me tell you one thing, what will be the final temperature of these two blocks. So suppose I have two bodies at different temperature which has some different specific heat at different masses, then what will be the final temperature? So this is m1 is the mass of this body, s1 is the specific heat, t1 is the temperature of this body, m2 is the mass of second body, s2 is a specific heat, and t2 is the temperature. So from T1 to T2 they will acquire a common temperature after some time, exchanging the heat between both between these both two bodies, depending upon which temperature is greater than T2. So if T1 is greater than T2, so there will be heat from T1 to T2, heat flow from T1 to T2 unless and until they get a common temperature. So that common temperature Tf is given by M1 S1 T1 plus M2 S2 T2 divide by m1s1 plus m2s2. You can check the dimension. The dimension is of temperature, and this is a very valid. Um, it's true, but you have to do a lot of calculations to get over here. So I'm just writing the final expressions for these revision classes. So now you can calculate the change in entropy for one. So what will be the change in entropy? dq by t, and your t, the uh, range of temperature will be from T1 to T final, and similarly del S2 you have to calculate from T2 to T2 final, and accordingly you will get the negative sign overall because uh, TF1 is for T, for the second body TF is at higher temperature, and for the first body TF is at lower temperature. Okay, so overall sign you will get, and limit will be from T1 to T2F, and for second will be T2 to TF. Okay, so that was the change in entropy for these two processes. So there can other process can be happen which are conversion process. Okay, so like suppose you have body at any temperature T1 and has any specific heat S, and that changes temperature from T1 to T2. So then what will be the change in entropy? So these are called conversion processes. Conversion processes. So for conversion process can be happen at first when the temperature of a body, let's call this mass to be the m. So m is the mass of the body and s is a specific heat, and the body changes its temperature from T1 to T2. Then what is the change in entropy? So delta S, change in entropy, is change of heat, that is ms delta T, ms delta T by which temperature? So this I have just calculated from the previous. So let me call from temperature T1 to T2. So this is log of T1 by T2. Okay, so this was just the previous expression, just to remind you that this can also be happen in a conversion process. Now, second conversion process can be take when there have a change in state. Change in state. Change in state means solid can become liquid or liquid can become gas. Specifically, I am talking about ice can become water and water can become vapor, specific for the system. So when we have from ice to water, there is a phase change at 0 degree centigrade. When you have this conversion, phase change at 100 degree centigrade. So this phase changes happen at a constant temperature with an energy that is supplied to change this, what we call this as phase transition. Okay, so the energy that is supplied is m times the latent heat. So your delta S will be integration of dq by t, since temperature is constant at these types of process, so 1 by t into ml. So the total heat supplied is ml. So delta is ml by t. So that is the conversion process when there is a change in state of a system, or a body has a specific heat and it goes from one temperature to another. Okay, so these are two conversion process, and above were when they were in contact. Now let me calculate the entropy of a perfect gas, and this is equally important because sometimes you just have given the value of Cp, Cv, Ct and volume and pressure and temperature, and then you have to calculate the entropy for a perfect gas. Okay, now let's just study the topic when we have a change in entropy for an perfect gas. So this topic is entropy change in perfect gas, perfect gas. So for perfect gas, what we mean is that follows this equation, that is PV is equal to nRT. If we specifically talk for 1 mole of gas, then PV is equal to RT. Okay, now from the first law and second law of thermodynamics, we have that dq is equal to du plus p dv. From second law of thermodynamics, we can substitute this dq to be TdS and du to be Cv dt plus P dV. Okay, so we have won this equation, or even I can substitute this a little bit more. So ds is Cv by T dt plus P dV by T. Okay, we have finally this equation from first law and second law of thermodynamics, and from the ideal gas law or the perfect gas we can take a total derivative of this equation. So what will we get? P dv plus V dp is equal to, R is a constant, so R dt. Okay, and we have second this equation. Now using these two equations we will calculate different forms of change in entropy processes when we have given a different data. So what different data can be? Suppose I have a value of temperature T1 and T2 and V1 and V2. I have only this set of information. Or I can have T1, T2 or pressure 1, pressure or pressure 2. P1 and P2 just denote two different states. So suppose I have an perfect gas at temperature T1, volume V1, and something happens and then it goes to T2 and V2 in this sense. Okay. So we have either this information or this information, or we may have this information that if we don't know the temperature, we just know the volumes of this states and the pressure of the states. So what will be the change in entropy if I go through these various process, either A or B or C? Okay, so what we are going to do, we are just going to use this equation and this equation to find the change in entropy of this perfect gas. So first is very straightforward. How it will calculate, we just integrate with respect to this variables. So what will we get, the change in entropy will be cv times log of t2 by t1. So because we have gone from t1 to t1 to t2, and this p by t we can substitute from here. So p by t will be r by v, so this will be r log of v2 by v1. So this will be the one expression for a change in entropy process when you have given this set of data. So this is for A process. Now for B, you have T1 and P1. So you have this temperature and you have this pressure, but you don't have the value of this dV. So what I'm going to do, I'm taking this PdV value from here. So I will change PdV as RdT minus VdP. Okay, so my RdT comes over here upon temperature, so this will be Cv plus R by T, so this will be Cp. So I'm just writing the final expression, you can work it out. So delta S will be Cp by T, sorry, this temperature will be on logarithmic, so this will be T2 by T1, and there will be a minus R log of this will be pressure in terms of pressure. So we have P2 by P1. So this is the second form. So this is for expression specific B. So this is done. Now we don't have temperature and pressure, we just have the value of volume and pressure. So see here it is dt. So you substitute the value of dt from over here and use this equation. So you can work it out, and this delta S will be Cv times log of P2 by P1, log of P2 by P1 plus Cp times log of V2 by V1. So this will be the total change in entropy for three different processes when you have different type of information given. So you can work it out. So you're just playing around this equation and this equation and this equation. Okay, so you just have to play around three equations and you get the different values of change in entropy process. Okay, so this was all about the change in entropy for different process when we have bodies in contact, or we have conversion process, or we have entropy for a perfect gas. Now let's move on thermodynamic potentials and Maxwell's equation. So our next topic is thermodynamic potentials and Maxwell's equations. So okay, so let me just define one by one and give you a short introduction to all these thermodynamic potentials and how to remember this Maxwell's equation and all. So the first thermodynamic potential is your internal energy. Is internal energy. Internal energy is represented by a symbol U, and we know that du is dq minus dw, or you can write du as tds minus pdv. So that is basically the first law of thermodynamics. So just a short introduction to this thermodynamic potentials. The second thermodynamic potential, so let me call this as one equation one. So the second thermodynamic potential, we call it as enthalpy. Enthalpy is usually represented by H, which has a form that enthalpy H is equal to U plus PV, that is internal energy plus P into V, pressure times volume. If you take the derivative, so what will be, dH is equal to du plus P dV plus V dP, then substitute this du from over here, so this is TdS minus P dV plus PdV plus VdP. This will cancel out, so you will get TdS plus VdP is equal to dH. Okay, that is the second change in enthalpy process. You can calculate it from here. So this is the second equation. And you can note, if constant at pressure, if P is equal to constant, so if P is equal to constant, dP is equal to 0, then your dH is equal to Tds, and that is nothing but dq. So from here you can have an intuitive idea what this enthalpy change will represent. So the enthalpy changes represent the total heat that goes out of the system or goes into the system at constant pressure. Okay, so this is also clear from this expression. I have not defined what dq is. So dq is change in the energy that goes out of the system or the energy that goes inside the system. Okay, so that is have an intuitive idea about the enthalpy. So it's just change of energy at constant pressure. Okay, so we have defined the second thermodynamic potential. Let me define the third thermodynamic potential, which is nothing but we have defined internal energy, enthalpy. Let me define the Helmholtz free energy. That is Helmholtz, Holtz, free energy. It is usually represented as F. F is defined as U minus Ts. So when you calculate do df du minus tds minus sts, you will finally get this equation df is equal to minus pdv minus sdt. And I will tell you the way how to remember these equations very quickly. Okay, so okay, this is the Helmholtz change in Helmholtz free energy in terms of volume and temperature, pressure and entropy. Okay, just for the side note, so what does this Helmholtz free energy do? So this Helmholtz free energy puts a limit on the work done by a system. So I'm not going in detail how it will put the limit and what will be the limit of that work done. So, but the intuitive idea is, just for a side note, that this Helmholtz free energy puts a limit on the work done by a system, that a system cannot do this much of amount of work. So that limitation on work done is done by this change in Helmholtz free energy or the decrease in Helmholtz free energy. Okay, so we have defined Helmholtz free energy. Now the fourth one is your Gibbs free energy. Gibbs free energy. Energy. So Gibbs free energy. So Gibbs free energy is defined as G. It is defined by U minus Ts plus Tv. Remember the forms of these equations. Internal energy is U, enthalpy is U plus Pv, Helmholtz energy is U minus Ts, and G is U minus Ts plus Vv. So you can manipulate this form. You can write U minus Ts as U plus Pv as H minus Ts, or you can write it as F plus Pv. Both all are correct. And you can substitute dg to be minus stt and plus vdp. You can work it out and you will get these final equations. Okay. So sometimes in JAM exam, they will give you several equations of this dh, df and dg, and they will say which one is correct or which one is incorrect. So you have to find out the correct and incorrect form. And here also the Gibbs free energy also represents something like this. Helmholtz free energy restricts the amount of work done by the system. The Gibbs free energy restricts the amount of non-PDV work done. Non-PDV means that the work that is not done by PDV kind of expression. So we have work done that is P multiplied by dV integral. So that is the other work. All the external work done is restricted by this Gibbs free energy. Now let me tell you a very short trick how to remember these all four thermodynamic potentials and these expressions, because you cannot uh, remember all these expressions at a time. So this is just a trick. This is thermodynamics square. Dynamics square. So this is nothing to do with physics. This is just a trick to remember this. So you construct these types of squares. You write the form, just write it somewhere, that good physicists have studied under very fine teachers. This I have read somewhere and I'm again quoting it over here. Okay, so different persons can give different perspective to remember this. So just take the first word G, P, H, S, U, V, F and T. Okay, and fill it from over here. So you fill this G, P, H, S, U, V, F, T. Okay, put two negative signs on pressure and this S. So whenever we have these S in terms of ds, okay, forget about it. So just put two negative signs over here. Now I am writing the first equation, that is for du. So I am writing this equation u. So my du will be equal to, take two diagonals term as the numbers and the other off diagonal terms in dv terms. So you can take this diagonal term and this diagonal term, so you can write minus p and t. The diagonal term of p is v, so write dv plus the diagonal term over here is minus ds, but you have to write only ds when this negative sign is only for these quantities, okay, not for this ds and dv. So this is just a convention how you can remember these things. Okay, so this was for du. Now let me write for second one, which was dh. So dh, so here is the h. Two diagonally opposite, write it as it is. So these are v and t, so v and t. So V, the diagonally opposite is minus P, but you have to write dP. So there will be no minus sign consideration. T, the diagonal is minus ds, so you will write it as ds. Okay. Now the third one is your G. So I will write it as dg. So this is over here. Two diagonally opposite as it is. So minus S and V. So minus S and V. Now for minus S, the term is dt. So this is dt plus v, the negative, the diagonally opposite is p, so dp. So these are the term. And the fourth one is df. So you can again, df is minus s minus p, so this is minus s minus p, and ps corresponds to dt and p corresponds to dv. So these are the four thermodynamic potentials. Even I have not considered one thing, the chemical potential and the number of particles. If that is the case, if there are, suppose du is sorry, this dh, dg, df, du are returns in terms of chemical potentials, then for these four equations you just add one term, that is plus mu dn plus mu times dn. Mu is a chemical potential, n is a number of particles, plus mu dn plus mu dn. If given in the data that you have to consider these equation in terms of mu and n, then only. Okay, so that was about the thermodynamics square. Because I want to finish this topic over here, so this video is going a little more longer. So now I will give you how to remember the Maxwell's equations. This is the way how I remember this Maxwell's equations. So you know there are four Maxwell's equation and they contains these terms, that is S entropy, P pressure, T temperature and V volume. So remember this order SPTV. Okay, this order is SPTV. Now write this SPTV in this way, S P T V, and one combination will be S P T V. One is clockwise and one is anti-clockwise. So you are starting S with the, if I consider to be a quadratic quadrant, so you are starting S with the first quadrant. Here over first quadrant. Now start S from the that is called the fourth quadrant. So S P T V, or you can have a different combination, that is S P T V. put the derivatives. So that is del, sorry, uh, del s by del v, del p by del t, del s. So put del every. Now you have to put a constraint that which derivative is taken care, the differentiation is with respect to which constant parameter. So this differentiation is at constant temperature. This differentiation is with constant volume. So this temperature from here and volume from here. This is with constant temperature. This is with constant pressure. This is with constant entropy. This differentiation is with respect to constant pressure. This is with constant entropy. This is with constant pressure. So this differentiation is with respect to constant with this parameter. This differentiation is constant differentiation with this parameter. Now the only things left is sign. So sign comes from the order we have written. So we have written SPTV. So just remember this order. We have written SPTV in this form. Okay. This is SPTV in opposite form. So this is written in this SPTV. So this is counterclockwise. This SPTV is written in clockwise. This SPTV is written in counterclockwise. So here the convention is that anti-clockwise represents your negative sign. So the anti-clockwise is this. So here you will have a negative sign. Anti-clockwise is this. Here you will have a negative sign. So your expression this del s by del p is minus. So this expression will become del s by del p is minus del V by del T. So this is at constant temperature, this is at constant pressure. So this is your one of the Maxwell's equations. Similarly, this will become del S by del V at constant temperature. This is del P by del T at constant volume. This will become del T by del P of constant entropy, del V by del S at constant pressure, and this the final will become del V by del T at constant S is equal to minus del P by del T at constant temperature. So these are the four Maxwell's equation, and this is one way to remember these Maxwell's equation. I have read this way in some book. I don't remember which book was in my undergraduation. So this is how you can have a better idea to how to remember this, but this is the one which I know and which I have followed to remember these Maxwell's equations, and that's it. So you can remember, but just remember that anti-clockwise represents your negative sign. That's it. And this is very confusing because most of the time anti-clockwise we take in physics, we generally take it as a positive, but here you take as a negative. Okay, so we are done with writing the thermodynamic potentials and Maxwell's equations. And in the next video, we are going to have a discussion on phase transition. We will discuss very short first order phase transition, second order phase transition, what are its different graphs looks like, and we will specifically look this phase diagram of water and CO2 and the Clausius-Clapeyron equation and application to Clausius-Clapeyron equation of various melting point and effect on boiling point and so on. So this will take around 20 minutes, I guess, to complete the phase transition part. So uh, after that, after the phase transition, I'm not sure that for this JAM 2020 I will be making the video on statistical mechanics for revision because the time is today is 6, so you have exam on 9, so there is no uh, this it is not advisable to study on ninth, sorry, on 8th. Okay, so you don't study on 8th, so still you have 2 days. I will try to post the next video by tomorrow. Thank you.